lecture today. We call that the ANCOVA in the presence of violation. I told you the other time, statistics. Oh, before I go into that, I've already posted the midterm 2 practice question, which is a midterm 2 exam written in the fall. I promised to upload the midterm 1 solution, but there was one student who wrote exam online, and the student mistakenly sent me an empty message, like no document attached. And all this why I've been sending, I think I sent message to the student to send the document, because if I should go ahead and post the midterm 1 solution, if it is already in the public domain, then it means when that student send me the booklet, there's no way I'm going to grade it, because the solution already in the public domain. But with this morning, when I checked, I sent a message to the student yesterday, and when I checked this morning, the student has already sent the exam document. So which means today, I'm actually going to also upload the midterm 1 solution. So that is what has been delaying the posting. Okay, now I want to welcome you to another exciting statistical topic, ANCOVA in the presence of violations. On Wednesday, I introduced it to ANCOVA. We use ANCOVA, ANCOVA is an extension of analysis of variance, okay, situation where we are looking at the effect of categorical factor on the response, but there exists another potential quantitative factor that also have effects on, on the response. And of course, I told you on Wednesday that particular factor need to be adjusted before we can have a good result. But let me tell you this, just like every other statistical topic, every statistical model has assumptions. ANCOVA also has some assumptions. Now, what now happened, what we want to do today now, what happened, what is the consequence, okay, or when there's a violation using ANCOVA. Okay, don't forget, I told you the other time, if we really want to investigate how valid is our model, we need to investigate whether assumption hold. The moment assumptions are violated, you cannot trust your model. Okay, now that is exactly what we want to do today. Now, I said when the first slide, when treatment affects covariate, okay, one of the assumptions is that there shouldn't be a relationship between the treatment and the covariate. I'm going to say that again. If I'm looking at the effect of a factor on the response, and there exists a covariate, okay, we don't expect relationship to occur between the treatment and the covariate. I don't know whether you guys have heard about in regression analysis, there's something that we call multicollinearity. Has anybody heard about multicollinearity in regression analysis? I'm going to write that now. Multicollinearity. Multicollinearity is when the explanatory variables correlate. When they correlate, they basically going to cause a problem, and we need to fix that. That's what we're trying to say here. Okay, that there shouldn't be multicollinearity. We should have a parallel lines. The parallel lines indicate that, okay, what happened, even though they got different intercepts, they're basically going to have the same slope. But in the situation where, there's a violation of that assumption, then you need to do something. Okay. Now take a look at this. You are looking at the effect of the amount of, you are trying to look at the effect of a teaching method on a learning score. Of course, the teaching method is categorical here. It has 2 levels, teaching method 1 and 2. But you realize that there's a potential covariate that we call the amount of study time Don't forget, the amount of study time can also improve the learning score. You know that, right? Okay, now, what we're trying to say is that there shouldn't be relationship between the amount of study time and the teaching method. But how am I actually going to know if that happen? Of course, I'm basically going to use the same example that we used on Wednesday. You remember on Wednesday, we're looking at the effect of machine, okay, on the treatment. I think the treatment, sorry, on the response. I think the response was strength, right? Strength. You remember on Wednesday, we got response. Our response variable was actually strength, right? And of course, we have factor. You know, we have the only factor that we are considering is machine, of course, which is categorical. I think we got like three different machine, but at the same time, we realize that was a covariate, and that very covariate. I think the covariate was diameter, right? The covariate was diameter. Don't forget, the covariate that we're actually going to talk about must be quantitative. Covariate cannot be categorical. When the covariate is categorical, then you are no longer talking about ANCOVA. You are talking about two-way analysis of variance. Because the two-way analysis of variance is you're going to have a categorical factor A, categorical factor B. Okay, now take a look at what we're trying to do here. We just if I want to investigate whether a relationship exists between the treatment, what is the treatment here? Machine, right? And what is the covariate? The covariate is diameter. Okay, now this is the code, and this is the output. Okay, now if you take a you want to check if treatments actually affect diameter. And as you can see here, if you take a look at the p-value, I need you to look at the general p-value, not the individual p-value that has to do with the machine. Well, the general p-value here is 0.1742, right? Did you see the general p-value is 0.1742? Oh my God, it's 0.7142 is less, it's greater than any reasonable level of significance. And when that happens, then we basically going to conclude that the relationship is not significant. Okay, now this is when you draw the box plots of of the machine, putting into consideration diameter. Okay, now, but in our example, we realize that relationship does not exist between the treatment and the covariate, and because of that, there's no problem. But you know what I did in another example? I intentionally, created a situation where there will be violations. And that is what I'm trying to now. So take a look at. I said, now I will create an example where the treatment does affect the covariate. Because of that, can you see my data? Crazy. I created a new data set called crazy, but I really want to explain that, to you, like, okay, when there's a violation, so what do we do? Now, I created a data crazy. If you take a look at the data here, I use a crazy, right? But the data that I use on here is EX. Do you see EX? Okay, that data is fine, right? But I intentionally, for the purpose of teaching you, when there's a violation, then I intentionally manipulate my data set, that which called crazy. And what do you see? You basically, when I look at the effect of the machine on the diameter, of course, look at the machine is significant, which means the relationship actually exists, right? Which means relationship exists between the the diameter, between the covariate and the machine, which is a violation. Okay, now if there's a violation and you just ignore that, you don't care, and you decided to run the analysis of covariance as usual, You know, running the analysis of covariance as usual is you're testing the effect of machine and that is, you know, adjusting for the diameter on the strength. What do you have? The machine is significant, right? You can see the result. But initially, on Wednesday, when we run that, you're basically going to see that maybe we have a different result. And let me tell you this. I used to tell, I used to say this all the time. It's not as if our module are failing us. Our modules are not failing us, but we are the one that we're not doing the right thing. Okay. So when there's a violation of absorption and you ignore that and you go ahead and use your module, whatever recommendation that will come from that module will never see the light of the day. And that is the reason why at times some policy don't work. Why? Because maybe the people that the decision maker actually apply, they actually apply the recommendation from experts who use a wrong model, who refuse to follow assumptions. Okay, now still using the crazy data, you can see the difference. The crazy data, the p-value is very, very small, just like what I said, which indicate violations. And when there's a violation, I don't think this is basically going to give the same slope anymore. Okay, with what I'm seeing now. Okay, now, if that happen, then what are we going to do? I said a new covariate model will be needed when the treatment affect the covariate. Now, do you know what I'm discussing now? There's a violation. How do we fix it? Within the framework of the analysis of covariance. That's what we want to do now. Fixing the problem. There's a problem. Okay, want to fix the problem. So a new covariate model will be needed to fix the problem. And in the new covariate model, I said what needs to be done is that the covariate needs to be modified. It means that covariate is not in good standing. I'm basically going to say the covariate is not in good statistical standing. Before you can use statistical method, your data set have to be in good statistical standing. Okay, now so the covariate is not in good statistical standing and then need to be modified with the treatment means subtracted out. Oh my God, take a look at that now. We are getting a new deviation now. We are the Sij. What is my Xij? The Sij actually represents the covariate. So what am I doing now? I'm actually going to be subtracting the treatment mean from that. Okay, and when I do that, we can accomplish this by fitting a model with the covariate as a response. Look at that. Covariate as a response. Okay. Now, when we do that, from any linear regression model, we can get a residual, right? Residual is just the estimate of the error, right? Of course, when you have a linear regression model, the estimate of residual is the difference between the actual response and the predicted response. I think you know that. Y minus Y cap. Okay, Y minus Y cap, that is the E cap, right? The actual response minus the predicted. But the model that we actually suggested now is that we need to fit the covariate X on the treatment. Then when we fit the covariate, why are we fitting the covariate S on the treatment? Don't forget, relationship shouldn't exist between the covariate and the treatment. But now that the relationship exists, how do we fix the problem? Now, fixing the problem, what we're basically going to do is we false regress the covariate as the response variable on the treatment. And from the model, we're going to get residual. Now, the residual from the model, okay, will be adjusted by the covariate. Okay, now use the residual from the above model in place of the original covariate. Oh my God, look at what we're doing now. This method is looking like a method of instrumental variable. I don't know whether you've heard about instru. instrumental variable. It's looking like that, where I'm no longer going to use the covariate anymore, but I will first fit a model where covariate is going to act as a response and the treatment is going to act as a predator. Then when I feed that model, then I'm going to get the residual from that. Then the residual from that model now, use the residual from the above model in place of the original covariate. It is the residual from the model that will replace covariate. I'm going to answer this question now. In linear regression, we normally say there shouldn't be relationship between the explanatory variable and the error, right? But now, we have computed the residual, and the residual is now going to replace the covariate, right? Of course, when you do that, there's not going to be any relationship between the, that and the treatment. Now, then in your module now, we're going to have adjusted covariate plus the treatment. We are no longer having the previous covariate, but what has replaced covariate now is the residual. Where do you get the residual from? You get the residual from fitting linear relationship between the original covariate and the treatment. Then this analysis compare the treatment each at their own average diameter instead of the common diameter. Now you need to estimate that. Now let me show you the output. Treatment highly affects covariate in the first place. You know that was little violation. Because of that, the covariate needs to be adjusted within its treatment. And this is the code to do that. Okay, the LM will regress the diameter with the machine for the purpose of getting what? Residual, right? That is that. COV.affect.treatment less than minus LM, the linear model. Okay, diameter on the machine. The diameter here is the covariate, right? That was having an issue, right? Then from this, we want to get the residual. How do we get the residual? Look at that, residuals into COV.affect.that. And after that, you write that code, you have that. Oh my God, what we have now, if I now want to run a new model, ANCOVA model, look at what I'm going to use. Do you want to see module.3? It's going to be strength, which is the response. Then on COV adjusted, am I still using the original covariate? No, but I'm actually using the covariate adjusted. What is the covariate adjusted? Residual. Residual from where? Residual from the module where you regress the original covariate with the treatment. Any question on this? Any question? Can we see the result? Let's see the result right now. Oh my God, this is the result that we have now. This result can be trusted. This result can actually be trusted. So you can see now, okay, what we have. And somebody may want to ask me, how do we measure intervention? How do we know? Using residual in place of the covariate, we actually work. I needed to look at the last result. I needed to look at the last result. In the last result, ANCOVA into module.3, where the response variable is strength, right? The response variable, where the response variable is strength, okay, and in the result, you are not using the original covariate, but you are using the adjusted covariate. You can see that. But the only way, if you really want to know whether your intervention has worked, okay, I'm going to award an extra credit now. Can somebody suggest to me, if I really want to know whether we have fixed the problem, can somebody tell me what we're going to do for extra credit? We adjusted the covariate, and in the new model, we're no longer using covariate, but we're using the adjusted covariate. The adjusted covariate was the residual that we estimate from the model that relates, the covariate with the treatment. So can somebody tell me, what do we need to investigate to show that the intervention has really worked for extra credits? We use error function to generate again. You kind of very close. Okay, if you really want to know, how do we know? What do we do to know that there was a problem in the first place? We did something. That is what you're going to do again. What do? We look at the relationship between the treatment and the covariate, right? Is that not what we did? I'm going to take you back to what we did. What do we do here? Look at it. Look at the force output. What do we do? The force output. What do we do? This is investigating whether absorption hold between what and what. Between the diameter and the machine. The diameter is the covariate. Machine is the treatment. And what do you see? The p-value. That is significant, right? That is what you're going to do again. What are you now going to do at this time? What you're going to do if you really want to know whether your intervention work, then you now regress adjusted covariate with what? With machine. Because the adjusted covariate should not correlate with machine if you really want to justify whether your efforts really work. Does that make sense to everyone? So the same way that we actually investigate is the same way we're going to investigate again. Okay. Now, you can now take your decision on this now, as this can actually be trusted. I always give two-way solution. The first one is the one that you use a linear, that up one is a linear regression approach. The second one is the ANCOVA approach. The two we actually agree. Okay, now, so which means with the adjusted now, when you make that plot again, everything is going to look so fine. Now let's look at the comparison of models. Okay, ANCOVA, somebody can decide to say, okay, you know what? I'm going to ignore covariate. I'm not interested in covariate. Of course, it means that person will do ANCOVA, right? That person will do ANCOVA, right? And somebody can say, okay, I'm interested in covariate. But when you are interested in covariate, you need to be able to investigate whether absorption hold. If absorption fail, then your ANCOVA will be wrong. That's why I say ANCOVA wrong and ANCOVA right. What is the ANCOVA right? The ANCOVA right is when I've already fixed the problem. There's a problem and I fix that and everything's fine. But let me tell you this. What is the price that we always pay whenever there's a violation I will ignore? That will affect the efficiency of our model. And what do we use to measure efficiency of the design? Is the mean-square error. I'm going to say that again. Mean-square error is a measure of efficiency of your design. And that is the reason why I'm trying to display that now. Okay, the likely issue. Okay, other covariate, we can actually have, there are other covariate model to consider beside a single line. Number one is separate line models where treatment affect both slope and intercept. I think I mentioned that in the other time in this class. And at the same time, we can have more than one covariate in a model. The example I've been giving you is just one covariate. Okay, I remember what I worked on in one of my projects when I was doing my bachelor in Africa. I think I work on multi-covariate analysis of effects of some selected feeds on the weight gaining ability of pigs. I collaborate with a friend of mine in veterinary medicine department. The guy likes pig, he works on pigs. You know, it's good as statistician, we work together with those in the field so that I need the data. She need information. I also need data. We work together. You know, we're trying to look at the effect of some of selected feed on the weight gaining ability of pig. And one of the covariates was the initial weight of the animals. You don't consider the final weight alone, you also consider the initial weight. And I also consider some other covariate too. So which means you could have more than one covariate. Take a look at this. Do you know we can have a situation where, you know, I said parallel or separate line models. Okay. Now check if parallel line model is adequate. What do we mean by parallel lines? Oh, how do we investigate for parallel lines? Now, take a look at this. In the analysis of covariance, we have two major assumptions. There are two assumptions that distinguish ANCOVA from ANCOVA. I'm going to say it again. ANCOVA has all the assumptions of ANCOVA, and it has additional two. Number one is there shouldn't be any relationship between treatment and the covariate. Not only that, you know, when you want to test about, another one is they should be parallel. We should have a parallel lines. How do I test whether we have parallel lines? What is the meaning of parallel lines? They should have the same slope. How do I test whether there's a violation of that assumption? Oh my God, the only way to test is to test for interaction. To test whether interaction is significant. And that's why I take a look at now. What am I doing? I'm considering strength on diameter, machine, and the interaction between machine and the diameter. If the interaction is significant, there's a violation of a parallelism, which means you shouldn't assume the same slope. Now, take a look at this. Is the diameter machine significant? No. Therefore, the parallel slope assumption work. I told you there are two major assumptions. Major one. Okay. Now, as you can see, which means, and that was why I said the p-value for that interaction is that it's not significant, and the parallel line model is adequate. Okay. Then I gave other ones. I gave, you know, using another data set. You can see diameter machine is significant here, right? And when it is significant, what happened? The parallel line assumption does not hold. So take a look at that. Okay, I think I put some, this is what I've done before, you know, adjusting. Okay, you also adjust the summary, you know, consider single line, parallel line, separate line, and so on like that, which is going to be the head of my lecture today, just like what I said. Anytime I give assignments, I will always review that with you. And I want to appreciate, you know, those who have been giving me feedback. What keep me going when I'm teaching is to hear from my students. When I don't hear from students, that is dangerous. I want to continue to hear from. Oh, go ahead. You want to ask a question? Oh, who is talking? Is it you here or here? Oh, okay. Yeah. Okay. Any question before I go today? Any question?
There are some questions in the chat.
Oh, question in the chat. Thank you so much. I'm going to check that now. Oh, somebody said how to calculate variance with two-factor without interaction. Yeah, without interaction, it means you are not interested in the sigma square AB. Okay, you are not interested in the sigma square AB. Okay, and somebody said, can we find the formula in the PowerPoint? Maybe what I'm going to do today, I'm going to send you a formula for that, but you're just going to exclude. Okay, and somebody said, when is the second midterm? Of course, the second midterm, check the syllabus. The second midterm is on the syllabus. The date is on the syllabus. How can you modify the covariate without affecting the integrity of your finding? You know, modifying covariate will not affect the integrity, because we need to modify covariate, because whatever we actually want to use, component we want to use in statistics, we have to play by the rules. Assumption is the key. Assumption is very, very important. Okay. So anytime there's an issue, what we do in statistics is transformation. But we know that when you transform, there may be lots of originality, but on average, we're still going to take a reasonable result. I think I understand your position that modification could tamper with the integrity. But without modification, there is no way we're actually going to move forward. I understand the fact that you know, there could be lots of originality, but the originality is not going to be totally lost. Information will not be totally lost. In the end, we're still going to have a reasonable conclusion to make. So modifying covariate will not affect the integrity of our findings in total. On average, we're still going to have a reasonable result. I think I like somebody who asked that question. Oh my God, you made my day. Well, that's a pure research question. Okay. Make sure you stay safe, guys, and have a lovely weekend. So bye for now.